All right, so you may notice at this point that we have covered two of the three types of reactions. We've talked about precipitation reactions, we've talked about acid-base reactions, and this is going to be a continuation of the acid-base discussion. As you can see on this slide, it says, extra info, what really happens in a polyprotic acid reaction. Ooh, it sounds very exciting, I know. Just as an FYI, we will not be covering electrochemical reactions, which are the redox reactions, in this unit. In fact, that will come in next unit. So this is, again, just a continuation of our acid-base reaction discussion. Okay, so the first thing that we need to know about as we start thinking about these acids is how many hydrogens are there. And this is where the whole polyprotic thing comes from. So there are three words that we need to be able to understand. First is a monoprotic acid. And I want you to think about those word parts for a second. Mono and protic. Chances are good you probably know that mono means one. But the word protic, that means proton. And a proton, as it says, is also known as, or slash, it's a hydrogen ion. A hydrogen ion, if you think about it, hydrogen has a proton and it has an electron. And if you create a hydrogen ion, you lose the electron and you're just a proton. So a proton and a hydrogen ion are considered one and the same thing. They literally are. So if you would look at some of these examples, you can see that HCl, or hydrochloric acid, nitric acid, or hydrocyanic acid, each one of these examples has only one hydrogen ion. Hence, it's monoprotic. Woo. All right. So then once you move past monoprotic, you move into what's called a polyprotic acid. So poly, the prefix means many. So when you start talking about polyprotic acids, we are talking about not, of course, monoprotic, but something that has more than one proton. And then FYI, the bullet point here that I forgot, straightforward reactions, nothing special. What I mean by that is that if you're going to be asked to write a reaction of, say, hydrochloric acid and sodium hydroxide, it's going to be completely normal, totally straightforward, absolutely nothing different. You may then be able to see the foreshadowing here that if you move into polyprotic acids, that we are in fact going to see a little bit of special stuff going on. So here we go. First, under the polyprotic heading, we have something called diprotic. What do you think di means? Right, it means two. Easy. So diprotic acids have two protons, and examples would include things like carbonic acid, H2CO3, or sulfuric acid, the H2SO4. We also could have triprotic acids, which is acids that are going to have three protons. And you don't typically see a lot of these because there aren't a lot of anions that have a -3 charge that would require the three hydrogens. However, phosphoric acid, as you see here in the example, is your most common triprotic acid. And we'll do some work with the phosphoric acid here in just a little bit. So the foreshadowing then comes kind of full circle here. If you're going to write reactions that include di or triprotic acids, you're going to have to know a little trick. That ends up being really what this presentation is all about. This is, again, the reactions unit. So we talked about the acid base. Now we're going a little bit further. And how do we write reactions with these polyprotic acids? All right, so here's how it goes. What I'm going to do first is show you what is called successive deprotonation. And I'm only going to use the acid to start off with so you can see just the basics of it. So first off, break down the phrase successive deprotonation. To have successive something means that you're doing one after another, and deprotonation, of course, means to remove a proton. So if we have a polyprotic acid, successive deprotonation means that first I'm going to take off one proton, and then in a second step, I take off the second proton. And if I had a triprotic acid, it would take a third step to finally remove the last proton. So successive deprotonation. So if I just focus in on an acid all by itself, it would look something like this. So notice here that I've got phosphoric acid, a triprotic acid, and that as I do the reaction, as I begin to break down this triprotic acid, that the first thing I do is I just strip off one little proton, one H plus. And if you look at what I have remaining, the H2PO4 negative, hopefully that makes sense to you why that would have to be the case. If you understand that the phosphate ion, the PO4 3 negative, it has that 3 negative charge. So when you have 3 hydrogens, the charge completely balances out and everybody's 0 and there's no charge on the overall phosphoric acid. But if I remove a hydrogen, I'm essentially now going to have an imbalance in charge. So my -3 that was here is only balancing with a +2, and that leaves that additional negative charge there. So hopefully that makes good sense to you. So this H2PO4 negative thing, as it says in parentheses, is called an acid salt. Remember the use of the word salt was anything that basically just considered, it was just considered an ionic compound. So this is not an acid, it's not a base. In fact, that's sort of a lie. It's both still an acid and is sort of a base at this point, but it's called an acid salt. So sorry, confusion. So as we move on to the next step of this successive deprotonation reaction, what you need to understand is that I've now, I have no more of the original acid, the phosphoric acid, that's gone. I now have hydrogen ions, and I also have my acid salt, my H2PO4 negative. This is what I start my next reaction with. So see it right here? So I just carry this down, and then I strip off another proton. And when I strip off another proton, I create a new acid salt that has a slightly different look because I now am down to only one remaining proton, and that also is going to change the charge. And I now have that -2 charge because I've only got one hydrogen to balance out with the original -3 of the phosphate polyatomic ion. So the final step of deprotonation with my phosphoric acid is now, again, same deal. Take my acid salt that I just created, and move it right down here, strip off my last hydrogen, and now look, I'm down to that final phosphoric acid. So a couple of things that I want you to note from this is that is sort of the way you can manipulate these chemicals, that when you take off atoms, or in this case, it's actually ions, that you have to adjust charges. And that's going to be something that's kind of important as we continue through with this. So again, this is just the acid. Notice that all I was doing was basically saying, hey, I'm going to throw this into water, and I'm going to allow the hydrogens to pop off one at a time. When I add a strong base to the equation, this makes it sort of a complete and full reaction. So it's going to get a little bit more dicey at this point because there's going to be a base molecule to consider. But please understand that I'm basing it off of what we just did up here. So you have the acid down already. Now we're just going to add in the base. So here is my full reaction, okay? This is my first deprotonation. So look at it carefully. Here's the phosphoric acid, okay? Now look, up here there was an H plus, right? And there was this H2PO4 negative. Well, my H plus is now right here. It gets wrapped up with water. And my H2PO4 is actually right here. Remember it had a negative charge? Okay, well, my base, NaOH, it's a strong base, so it will completely dissociate in water. My sodium will go with that H2PO4. Remember, it had the negative charge? Well, here's the positive ion that then balances the whole thing out, which is kind of cool just to see, again, how you can manipulate these things. The hydroxide that would have broken off is now right here, and it paired with the hydrogen from here that I stripped off. So, with the use of the arrow, maybe you can see then how that hydrogen is stripped away from the phosphoric acid, added to the hydroxide to create water, and then my remaining acid salt, the H2PO4 negative that we did up here, is now going to pair with the sodium to produce this chemical. Okay? All right, so now we, again, consider what I said before. We now have no more of this, and we have this. So this is the chemical that gets carried down to the next step. And I'm going to treat it with another dose of my sodium hydroxide, okay? So NaH2PO4, which is the acid salt that I created, and now I've got more of my base. So the same thing happens. A hydrogen from here is going to pop off and go with the hydroxide to create water. And now take a look at the new acid salt molecule that I've created. So I now have a second sodium that I have to use because this thing, the HPO4, well, look up here. Remember the charge was a -2? Which means I need 2 positives to balance it out. So you're just creating ionic compounds here with the available ions that would be in the solution. Okay, my final deprotonation reaction, again, I'm going to use the thing that I just created, this Na2HPO4, and that's going to be my starting chemical here in my problem. I give it another dose of the base, the sodium hydroxide, and the same thing happens. The final hydrogen here pops off, and it goes with the hydroxide to create water. And then now take a look at this chemical. This one should be a familiar one, Na3PO4. That is sodium phosphate, and it's put together in the same way you would have done sodium phosphate forever and a year ago. Na is a +1, PO4 is a 3 negative. Cross the charges, make your ionic compound, and voila. Now, what I want you to notice is that at the very end of this, we've now created something that is a completely neutral solution. We have now no acid and no base, but in the process of it, we had to slowly kind of go through this maze of stripping off one hydrogen every little time. So if you want to think about this in sort of a backwards way, the way that you would have done this last year, if I said react phosphoric acid with sodium hydroxide, you would have said the H goes with the OH to make water, and you would have said the Na goes with the phosphate to make Na3PO4. So do you see that right here and right here, this is the reaction you would have written last year, or really up to this point. These in the middle steps, these intermediate steps, are the things that are actually happening in the solution. So you can see it's quite a bit more complex than just what we do in actual general chemistry to kind of get your feet wet. So, and just FYI, this tends to be kind of a tricky section for people. I generally have a lot of questions, so record your questions and we can talk about this as much as you need to tomorrow if you feel any confusion on it. Okay, so next, what I'm going to ask you to do is actually try it yourself. Write the molecular, and then something we haven't actually done yet, the net ionic equations for successive neutralizations, which is just a way of saying successive deprotonations of sulfuric acid with potassium hydroxide. One of the first things that I would want you to notice is that your sulfuric acid here is a diprotic acid, meaning that it's going to be deprotonated in 2 steps. And that we're going to be creating these weird HSO4 with, various negative charges, these kind of ions, just like with the phosphate we did last time. Remember, with net ionic equations, you're breaking apart ions, and it's important to understand also that acid salts are soluble. So anything that you create with a potassium and some variation of like a sulfate, that is going to be soluble, and you do need to break that into ions. So do me a favor, pause the video and try it. I will give you the answer when we return. Okay, so hopefully you at least gave it some thought, at least tried to jot down a few things on your paper. The first deprotonation would look like this. This would be the molecular formula. You have the sulfuric acid and your potassium hydroxide. The first H goes with the OH to create water. And then you have the K, which is going to pair with the remaining portion here. And it's going to look like this. Because again, when you strip off one hydrogen, this would have a single negative charge and would need the single positive to balance it out. Now for the net ionic equation, it would look like this. The sulfuric acid at the front here, this breaks down completely because it's a strong acid. This breaks down completely because potassium hydroxide is a strong base. Water is liquid, so it stays together. And then the KHSO4, that was an acid salt. And as I just said a second ago, that is soluble in water. So that's the way you break it down. And then I want you to notice how I'm going to cancel things out. Notice that I can cancel out the potassium and the potassium. That's pretty simple, right? Okay, then notice the sulfate and a single hydrogen with a single hydrogen and a sulfate. Okay, so see how you're kind of mixing and matching a little bit? And what that's going to create for you is, now remember, I still have a hydrogen left here. I have my hydroxide and I have my water, and I produce the net ionic equation of water. Okay, well, that should be sort of a no-brainer at this point, or maybe something that you're like, oh my gosh, yeah, of course. Sulfuric acid and KOH, they are both strong acid, strong base, and the net ionic equation is always going to be water. So even though there's a lot more ionically that's happening, the end result net ionic equation is still that of water. Okay, so for your second deprotonation, for your molecular reaction, you're going to use the KHSO4 as your starting point, which you can see here. You're going to hit it with some more base. You're going to, again, produce more water, but now you're stripping off that final hydrogen, and now you're just left with a sort of very typical potassium sulfate, K2SO4. And then if you, again, go back and break those things down, this is, again, an acid salt, so that is soluble. This is a strong base, so that's soluble. This is liquid water, so it stays together. And this is a regular ionic compound. It contains a group 1A metal cation, which means it is soluble, which means it gets broken down. And now we're going to go back and take a look at what things we can cancel out. So first off, do you notice that there's 2 potassium ions? Check it out. 1, 2. So all of that can get canceled. And then the sulfate here we need to cancel out, and we actually can do it right here. So we can do pieces and parts even by separating this out just a little bit further. And that brings us down to our final net ionic equation, which again is that of water. So again, record your questions if you have them, and we can talk tomorrow. Oh, yeah, sorry, I forgot about this one. Acid salts are soluble in aqueous solutions. So this is something I've been saying here within the last couple slides. So don't forget about that. We can break them into ions for net ionic equations. Okay, so final slide for the day is basically just sort of a helpful hint kind of a slide. Sometimes as you are reading your questions, as you're reading homework problems, that is, you need to pay attention to the wording. Am I supposed to write the normal reaction like I would have in general chem, or am I supposed to do this fancy way with all these successive deprotonations like we just learned? So I say in the first bullet point, sometimes there will be clues in the problem. Does it say write the reaction of the complete neutralization? Well, that means write it like normal. Write it like you're in general chem. Strip off every hydrogen and create a normal old chemical reaction. But notice in the third bullet point on the screen here, does the problem say something like, show the reaction for the removal of 1 acidic hydrogen? And again, if you're looking at the acid and it's a di or a triprotic acid, then that's going to be a successive deprotonation type of thing where you show 1 acidic hydrogen removed, which essentially means they're asking you to do the first deprotonation only. But really do pay attention, use the problem, use the wording of the problem to help you out. It will make a big difference if you read very carefully, okay? So when we come back to class tomorrow, definitely ask me questions, and then we'll see how the homework goes. So that is it for today. See you later. Bye.